Okay, so today we're going to talk about the parallel algorithms in C++, and in particular we're going to talk about Intel's implementation of it because they open sourced their implementation, which now GCC version 9 has incorporated into it. However, their open source implementation is available, and you can use it with any C++ 17 supporting compiler. And I should just mention, for those who are also using Windows computers on your own systems, Microsoft, the latest version of Microsoft Visual Studio does support that. So before we get into anything, let's take a look at compiler support and how we can find out more about that. So here, I'm going to open up a website called cppreference.com. It's an excellent online reference to everything in C++, and it covers the various standards, as well as increasingly there's a whole C section on it for C-related stuff and C standards that are relevant for the C++ language. So if you go to cppreference.com, and you click this link in the top left that says compiler support. So click on it, and you'll get a big page, and this page is in reverse chronological order. I should mention, some of you will say, what in the world is C++2A? Basically, the next C++ standard will be C++ 20, and until it's an official standard, the C++ committee will do things like 2A, where A is we don't know exactly what year. It might be 20. It could be 21. We expect it to be 20. Similarly, this was done for the first version of C++ after C++ 98 and things like this. So this pattern has continued, a number followed by a letter. If you see that, that means it's not yet a standard, but many compilers implement features in the language. So if we just scroll down just quickly on it, you can see on the top there's the various compilers. If you're using a compiler not listed, then it's probably a compiler you don't want to use. And red means it's not supported, and otherwise you see the version number of the compiler for each feature and which compiler and which version supports it. So this is awesome. So we'll just scroll down a little bit further because we're not worrying about the C++ 20 standards. And new to this page, they've added, besides the core language, they've added sections on the library features. So the C++ parallel algorithms came in with the C++ 17 standard. Now, the support for the parallel algorithms, that's in the standard library, and this web page, after the features of the language itself, they have a section on the library features. So if we scroll down to this section, C++ 17 library features, we'll see a whole bunch of features on the left, okay? And in particular, draw your attention to standardization of the parallelism TS, the technical specification, that item, and you can see here that the various libraries that exist, GCC and Clang have their own, Microsoft has their own, Apple has their own, Intel has that Intel Parallel STL, so they added a special column here and stuff like this. And you can see that GCC version 9 supports it, okay? Microsoft Visual Studio in version 19.14 supports it. Otherwise, you got to use the open source Intel Parallel STL with the Intel compiler version 2018 or newer. So strong recommendation, if you are using this feature, use the latest compilers. But if you're using an older compiler, you can use the Intel Parallel STL. So if you're using Clang and doing something and maybe using Singularity in it, then you can use the Parallel STL with Clang as long as you download the Intel compiler open source implementation, and then you can use it with Clang. And I'm going to show you a little bit of that in this presentation. So this page is very handy. Just to recap how we got here, cppreference.com. You can, of course, look up anything in the language, including the algorithms and that. Click on compiler support at the top here. And then once you're there, scroll down to the C++ 17 language features. Okay, because it'll start off with this and all this, go down to C++ 17 library features. So if I just do a quick search for that, C++ 17 library features, there we go. If you scroll down there, then you'll have that information. Okay, next step. If you do need or want to download, and you want to look at the code, whatever, the Intel Parallel STL implementation, you can just go to GitHub, and if you go to github.com/intel/parallel-stl, you'll be able to download it through Git. Okay, and you just click the link on the right here, and you can copy and paste this Git link into your Git client, and you can download the thing, and the instructions on using it are all provided there. Okay, so before I get into using the Parallel STL, I wanted to start off with talking about iterators, because a lot of people aren't entirely familiar with the algorithms in C++ standard library. They've existed since the first C++ standard, and how to use iterators. So I want to just do a quick overview of this and spend some time on this, because then it'll make sense on how these parallel algorithms work, and then whatever algorithms you want to use or create, and that you'll be able to explore those more meaningfully. So the first thing I'm going to do is I'm going to start off with a program, a simple program. It's going to be basically a C program. It will be C++ compiled, but it'll be a C program. And the reason I'm going to do this is iterators in C++ are based on C's pointers. And I want to show everyone how this is the case. And so if you already know how to program in C, and you're exploring C++, or you know how to program in C++, but you're not sure about iterators, but you have learned about pointers, then great. This is where we'll start, and then you'll see how the iterators work, and in the end it becomes easier to use pointers, because pointers are hard-coded to arrays, whereas if you're using iterators in C++, you can use any container. So a container can be a balanced tree, a linked list, an array. It can be any number of things, and C++ offers a number of these. So being able to do this is a big deal. So what we're going to do is write straightforward, mostly C code, but it will be C++ code. And for convenience, I'll do a using namespace standard here. And what we'll do, okay, is we will start by declaring an array. I'll call it AR, okay, and we will set it to an initial set of values. And yes, I am typing live here, so my typos and everything will be here. Okay, so now we have this array, and that's fine. You can say, okay, well, normally one would write a loop to output it, so they would typically go for int I is 0, well, I is not equal to, I got 5 elements here, plus I, and then you might go C out, and you output each array element. Okay. And of course, we'll output the here's return. So that's how you might write an array and spit it out. So let's just make sure this works. I'm calling this P1. Okay. And let's actually, for this right now, let's use GCC version 9. So we can get that. I'm on Graham right now, so we can get that by just going module load GCC 9.1.0. So we'll just load that compiler, so we'll use GCC for now. So we put G++ in the name of the program, and I got typos. Okay. So I will fix the typing mistakes. Okay. The array brackets I put in the wrong spot. Here we go. There we go. As always in C++, my recommendation is fix the first bug and then recompile, and all of issues might disappear. So in this case, that did happen. And if everything is good, then when I run the program, I have 1, 2, 3, 4, 5. Awesome. Okay. So that's nice. Now what I'm going to do is I'm going to copy this program. So if you want to ask questions later, you can refer to P1. And I'm going to copy it to P2. And I got this program. Now I'm going to point out that we could, arrays and pointers are equivalent just in C++ as they are in C. And so we could do this. We could say, I want, I'll call this the start. Okay. And the start of my array, for those of you more used to just using array syntax, I'll put the address of AR0, and the stop of my array, okay, is the address of the first element, so that is just start, and I have 5 elements. Okay. Now, this looks a little strange because you would say, wait a minute, if you start at 0, you want to go to 4 because 0 through 4 inclusively is 1, 2, 3, 4, 5 in that array. And I would say yes. But the C and the C++ standards permit all pointers to valid objects to point to one past the end of that object. So the AR array starts at index 0. It ends at index 4, because that's 5 elements. But it is legal for us to have an address of the 5th element, but it's not legal to look at it. Now that makes sense because there's nothing after the 5th element, so that would be bad, it would crash, or anything could happen there. But because of this rule, this allows us, so I have start and stop with my pointers here. This allows me to do the following. I can change my I variable to be a pointer, star, okay, and then I can put start instead of 0, and stop instead of 5, okay. And if I do that, now I'm using pointers, so I can delete the array at an index I, and instead, whoops, I can have star I to access that element. Okay, so this is the same program as before, except now I'm using pointers, and the same thing gets output. So just to quickly point out here, right here, that's the start, and that will point to this first element. This start plus 5 is effectively after the last element. But as long as I never look at that address, that's okay, that's legal. I only want to look at the addresses in the valid array, which would be a array index 0 through 4, and that would have 1, 2, 3, 4, 5. And that's exactly what I do here. I started at start. I go up to but not including stop. So I'm only looking at everything up to but not including stop. Just like when I did the for loop before, I had a 0 instead of start, and I go up to stop. And stop, though, before was 5. So I didn't actually access that 6th array element. So this is cool, because now, copy this to P3. Now we can start doing something. We can say, this is interesting. Okay. So let's make this array global. We're not going to really change the program. We're just going to shift where things are at. Okay. And what I'm going to do is I'm going to write a function. Okay. And I'm going to call this function start. Okay. And right now I'm just going to hard code it to return the start of the global array. Okay, and that was this value. So now we can delete start down here. To minimize space, I'll just cram this into one line. And then we'll want to do the same thing with stop. Okay, and what we can do here is we could do the same thing we did before. Just add 5 to start. If we come down here and replace start with the function call, and stop with the function call, we have the same program. Now, to go one step further, okay, we will use a type def. In C++, this is another way of doing a type def. And we will define the type def to be int star, a pointer. So we can use the word iterator. Here we go. And I'm going to change this down here. So now we have this code. So what we have is the same program as before, except I changed all the int stars to iterator, and it's a type def. So effectively, this could be hidden later. Great. I just say the word iterator, and I have an iterator, and then I have my variable, and I say start at some location, go up to, but not including some stop location. Okay, and I treat the iterator as if it were a pointer, so I just go star I when I want to output it. So if we compile this and run it, it should run the same. Oh, I got some typing mistakes. I was not declared in this scope. I'm going to call this iterator my iterator, because I have using namespace standard, and there could be things called an iterator in the library, and we should be good. There we go. Okay. So when you have a bug in C++ and missing template arguments because I didn't rename all my iterators, it's a good idea when you're trying out things like this and your code doesn't compile. If you've given something the same name as something in the standard library, or it might be the same, just put my in front of it, and if it all works, then that's exactly what the problem is. So we'll do that. Clear the buffer. There we go. So now if I run it, I'm good. I get the same output. So let's make one more change. Okay, so I just called it my iterator instead, so there's no conflicts. But now, in the standard library, instead of start and stop, the start and stop functions we wrote are called begin and end. So instead of running into some conflicts, I'm just going to put my begin and my end here, just so there's no conflict. And we'll start by doing this, and then we'll do one more edit. My begin, my end. Okay, so that was cosmetic. I changed the names. But the idea here is in C++, you go from the beginning to the end of something, and the end is up to but not including. So you can, if you have 5 elements in your array and you want to go through all of them, then the beginning would be the first one, but the end would be this one past the last one case. So you would never access what n points to, but everything else is fine. And that's the strategy. It's no different. What C++ does is lifts all these pointer manipulations into a thin veneer of functions and types. So here we have begin and we have end functions. They're hard-coded to this array right here, okay? But I don't have to necessarily hard-code them, okay? So we have this here. I'm going to save this and go to program 5, okay? So we don't necessarily have to hard-code our array. So what do I mean by that? Well, what I could do is I could have a version of begin, okay, and this version of begin can take some start position, okay. And this version of end can take some stop position. Okay, now while this might look a little strange, why would I remove that? Normally you don't have a global variable. So if we put this array back down here, then my begin becomes array okay, or if you prefer, we were doing the address of array bracket 0. And the end position, okay, would be the end position. So we could just do array plus 5. For pointer syntax here is better to use than the array syntax because we don't want to access the location. So using pointer syntax, you can just put AR. Arrays are always decayed into pointers. Almost always. So there we go. I passed in the begin and the end of my array. So if I did this properly, compile and run right, it did. Awesome. So now we go to this and we say, okay, technically here, you know, we can have the notion of begin and end. We're okay with begin and end at this point. There shouldn't be any compiler issues with this. Okay, and the only thing that also happens is this gets put into a class or a struct, and this is what you have for your array. Okay, so we'll make sure this program compiles first with that tweak. Okay. Compiles. Okay, so now what we want to do is, this is great, we can go from the beginning to the end with our hard-coded array. Okay, well, C++ has this thing, header file, many people see at some point, sooner or later, algorithms. We've got a bunch of algorithms. Okay, that's kind of cool. Now, we want to go through this for loop that we have right here, goes through and calls, outputs each element with a space after it with cout. Okay, well, there's an algorithm that does that in the standard library, and that's called ForEach. Okay, and ForEach works as follows. ForEach takes anything that's an iterator, this includes pointers, okay, and you start at the beginning, and you go to the end, okay, and now you want to put your function. If you've never seen a C++ lambda function before, you don't have to write a global function and call your function and pass the function, and you can do that, but you don't have to. It's easier just to write a function right in the code where you want it. In this case, the function we want is this C outline. Okay. You'll notice a little change, however. Okay, so let's take a look at this. And I'll space it out a little bit so you have these algorithm things explained. So the begin end business here, this means I start at AR, okay, and I stop at AR plus 5. Okay, that's cool. And I used square bracket and round bracket to represent that half-open interval. So all of the algorithms in the standard library use half-open intervals. You start at the beginning, whatever the beginning iterator is, and you go up to but not including the end iterator position. Okay. Now, this here is a lambda function. It's a function without a name. Okay. Now, when you use the algorithms, the lambda function will always be, or whatever function you pass it there, will always be passed whatever that element is. So the iterator points to an integer, as in this case, then that argument will be an int. If it points to a double, it'll be a double. If it points to a complex, it'll be a complex. It'll, whatever the type is. So nicely, with the lambda code, notice that the C out I just outputs the I. I don't put star I because the lambda is not past the iterator. The lambda function is past the value that the iterator points to. Okay, so this for each is equivalent. In fact, if you saw the definition of for each, it's a templated version of the for loop that I just removed from the previous code. So if we compile this, it should still compile. Right now, we're still using the original C++ standards implementation of algorithms. Okay, so we have that. It'll run, and now we'll copy it. Okay, so this is kind of cool. We have an array of 5 elements. I can call for each, and I can output them all. Okay, you might say, well, can I do more? Well, sure, we can do a lot more. One of the interesting things we could do is sort them. Okay, because that's also in the algorithm header. So we don't need to pass a lambda function with sort. We do need to say what the beginning and what the end is. And so here we go. Okay, and if I get rid of my comment, this actually looks really elegant. It's all nicely in one line. So begin to end. Okay, so let's take a look at this. And wait a minute, I still want my for each. Well, we can do that. I'll put my for each back in. So begin AR to end AR plus 5. And let's add in this C out that I removed. So I should have commented out my code, but that's okay. Retype it, and there we go. Okay, so this is pretty cool. I first will sort the array, and maybe we should not have a sorted array here. How about we put and there we go. So we have a bunch of values. We'll sort, and we'll do that. And then I'll do one more thing, and then we'll see how we can do stuff in parallel. Okay, so now I have all the values sorted. Okay, so that's kind of cool. You might say, well, what if you don't want to use your own hard-coded array and you want to use something in the standard library? I don't know, you want a dynamically allocated array. Well, then you can pound include vector. Okay. And all we'll do is we'll just reuse the same array here. And we will have vector of int, okay, and we'll have it in a variable called AR, just to not have to rename everything, okay. But what we can do now is go begin AR to end AR. We don't have to worry about the begin and end because the begin and end are already defined for this. So we can say the begin and end. We can fix this one here. Okay, and we won't need this stuff anymore, so let's just get rid of it. Okay, so now we have a vector. This is a dynamically allocated array. It's initialized to our 5 numbers, but it'll start at the beginning and go to the end. Okay, so now okay, and we can see that runs. So now let's do some magic. And the magic is this. In ISO C++, if you just go include execution, okay, and now that you have that, if you go execution : par, execution : par, so notice what I did there. I added an include file, and all I did was add an extra argument to each of the algorithms I want to use. Execution : par. Okay. Now, this code became, when I did that, C++ 17 code. Okay. But these are the parallel algorithms. So if you already have algorithms you're using and you want to make them parallel, then you can just add an extra argument and they will become parallel. Okay, it doesn't mean it'll execute ideally in nice, efficient parallel code, because you might have to rework some of your code for parallel execution purposes, but it will do its best to try to run them in parallel. So you can now think of the sorting as trying to sort in parallel, do the work in parallel. For each, do all the output work in parallel. Okay. There are some caveats, of course, to this, but for now, this is a good place to start. So what we want to do now when we compile our code is we want to specify that it's C++ 17, okay? And then we can do the code like this. When we compile it, if you get an error about this TBB include header, that's because GCC is using internally Intel's parallel STL implementation, and that uses Intel threaded building blocks. So you need to have Intel threaded building blocks installed. So module load TBB will do it on our Compute Canada clusters. And if you then try to compile, it'll be able to get that header, and then you'll get this big dump of .o lines here. In particular, notice this /temp/.o thing and all this mumble jumble stuff. If you get that, it's probably because you forgot to link in the Intel threaded building blocks library, which you have to do currently. So you put a -l TBB at the end of your compile line, and if you do that, it compiles. And you'll say, lo and behold, if we run it, will it still run? Yes. And what we can't see here is, and only 5 elements, it probably didn't even bother doing it in parallel, but what we can't see there is that it would do it in parallel, and if we had larger arrays, certainly, it would do that across multiple threads. So in a nutshell, iterators are based on pointers. This is cool. So iterators shouldn't frustrate anyone. They're just positions inside of a container, an array or a linked list or any of these things. And then C++ has a number of algorithms you can use. And to use the parallel version of the algorithm, you add an extra argument to the beginning of the arguments to that algorithm. Now, not all the algorithms have parallel versions, but the vast majority of them do. So that's what you can do. And then you just recompile your code, and you're good. If you take out that execution : par thing, it will run sequentially. Okay? So that's pretty cool. So now let's talk some turkey about, you want to make this work. How can we make it work? Okay. Well, I got an example here, and there's a couple cases. The cases I have are right here. If we want to use the Intel compiler, you can load the 2018 compiler or the 2019 compiler, but you got to go module load and then Intel, okay, and then run some options. We'll see what those are in a sec. Right now we're using GCC 9.1 and threaded building blocks, so you saw me use that. If you wanted to, you could use any C++ 17 compiler, and you load the threaded building blocks. There's a little difference in the code that Intel wisely set up so it would be relatively easy. So let's take a look at what that might be. Okay, so I got a short function here. This function has this special line right here, okay, and that's code that I've written. It amounts to doing one call to the Intel threaded building blocks library. And I'm going to show you that code in a sec. But if we made a vector of 10 million numbers, all set to 0.5 in this case, but you can change that, of course, and then we used the high-resolution clock from the standard and took a start time and a stop time, T1 and T2, and if we ran accumulate to sum up all the values, and the base case being 0, that accumulates sequential algorithm, okay, then we can output the time for it. We can do the same thing. The parallel version of accumulate has a different name. It's called reduce, but it's otherwise the same. We pass in the execution par option, okay. We do the same timing, so T2 minus T1, and then we output how long it took. So that sounds pretty good. Okay, so right now we have the Intel compiler loaded. So I have a makefile here. This will build it. Okay. So it took care of the includes and stuff like that. But now I got that. So now I got this ISO reduce command that can run. And there we go. I ran it. The accumulate, which is the sequential result, took 10 milliseconds. And the reduce took 4 milliseconds. You do it again. 14 and 2. I'm on the login node, but this is a very fast and small program, so it's okay. Normally you would SLOC and use it on a compute node because you're probably using more resources, or you're running this in your batch. But nevertheless, you're going to get times, and they will be pretty close to one another. They'll occasionally vary depending on what other multitasking your system is doing. If you're running dedicated on a node, then the timing will be very consistent. So that's how to do the ISO code. And you'll say, well, wait a minute. What's the trick if I'm using the Intel compiler, and what's the trick if I'm not using GCC version 9 to do my code? Because you're going to say, I don't want to change my code around. And fair enough. What I did here is I did a pound include par STL. Notice there's no pound include execution here. I could have done that, but using older compilers, that might be an issue. So par STL is a library I made. If I go into headers, okay, and it's in a nutshell quite simple. Okay, so this library does this. We need this one piece from the Intel threaded building block library, and we need to, when you run jobs on our clusters, you need to limit the maximum number of threads that will be used. Otherwise, the Intel library looks and says, oh, you've got 32 cores, I'm going to run 32 threads. But if you only said, I want this to run with 4 threads, that's a problem. So if you pound include this library file, okay, and do one function call, which amounts to a call that's down right here, on this line, if you do this right here, that line right there, okay, that will get you the default number of threads, which is probably not what you want, okay. In fact, you want to set it to something else, but if you got that number of threads, that's fine. You can pass that number of threads to this type in the Intel threaded building block. Now, if you do that, that's how many threads you'll get. But what if you don't want that many threads? Well, what if you wrote a function to get the number of threads, like I've done here? So you can pass that in right here. Okay. And what would you want that function to have in it? Well, you'd want that function to basically get environment variables that are set. Now, Slurm, to run your jobs, will set some variables, but just in case you're used to the OpenMP variable, how about OpenMP number of threads? Okay, so if that's set, fine. This one here, if you happen to have PSTL number of threads set, okay, we'll use it. But otherwise, we'll use OpenMP number of threads. If that one's not set, maybe you didn't set it or whatever, Slurm virtually always sets Slurm CPUs per task, so that will be the right value. But just in case, we will set Slurm CPUs on node as the value. So we'll read that into a variable called number of threads and return that from this function. So magically, if we just invoke this at the start of the program, then we're good. Okay, subject to some caveats with the Intel threaded building blocks library, but we're good. So what I did is I put all this in a class in a nice little constructor here, so that in the actual code, I could just create that object right here, and it will call the right function for me. One line, just a nice pound include in one line, and it's simple and easy. Okay, and this way, if I forget to say the number of threads, I'm okay, because it will look for those environment variables, and Slurm will always set at least one of the two listed, the Slurm ones, so it will always get set to an appropriate value. So this will allow this job to run properly if I were to put it in an SBatch script. An SBatch script could be done normally like you would do any other SBatch script for a threaded job. Okay, so before we go a little bit further, let me just show you how this works with Intel. So with Intel, I want this module load line instead. So we'll do that. So module load Intel, and my make file is set up that I can just go make Intel. Okay, and this will make an Intel reduce executable. So if I do an ls-l, I see I have an Intel reduce. There we go. Okay, awesome. And you'll say, oh, well, what if we're using an old version of GCC? Older than GCC 9, that is. Well, there's 8, as long as it supports C++ 17, we're good. So module load GCC 8, oh, that won't work. There we go, module load GCC 8.3.0. And then remember to do a module load on the Intel threaded building blocks. Okay, so now if I go make other in my script, which is set up, you're going to get some warnings. Okay, in the parallel STL library, but that's okay. It made the executable. Okay, and there's two ways of compiling it with OpenMP and OpenMP SymD. I'll just show you the OpenMP one, and if we run it, and it'll run. Might not run at the same speed or whatever, but compiler settings change and stuff like that, but you can see it run. And the nice thing is, I did not edit any source code there because of the way I did it. The other thing I put in that special header file of mine is this at the top. Okay, since I'm using this header file to give me the parallel algorithms, I put in this line at the top to say if it's greater than GCC 9, okay, include execution algorithm, numeric, and memory. Just include those. And par STL namespace. Okay, and I didn't talk about that. The one change you want to make to the code. And otherwise, use PSTL / those headers, and then this macro par STL namespace because it's in a different namespace. What Intel did is did their library in a different namespace, slightly different names for the headers. So if I go back to reduce, okay, the one tweak you want to make for reduce is with what I did in that header is this par STL namespace : because to use the Intel compiler or any other compiler with the Intel open source library, you have to put PSTL in front here. So I made a macro instead, so this way, no matter which one I compile it with, it'll work. So for example, if I were to go make other again, okay, this time it's going to use that result, and you probably will see better results. So somehow it compiled even though I didn't have all the include files, but now with this, everything's taken care of. So with this minor touch to the code of having to write a little macro, or if you want, you can put PSTL : you can use older compilers. So it's really easy to change your code later to support the ISO standard when more standards, or when more compilers have that implemented. Okay, so that's pretty cool. Okay, so what can we do? Well, we can do all kinds of things with the Intel Parallel STL. If we go back to the cppreference.com website, okay, you know what tasks you want to do, what tasks you want to compute. There are all kinds of algorithms. On the right-hand side here, there's this algorithms library link. So if we click on it, it gives you a summary page, and it lists. So if you've not explored the algorithms much, it's worthwhile just going to this page just to read what algorithms are there. Okay, and you can read them all, what their descriptions are, and what they do, and you find something that you like. So let's say it was sort. You can click on sort. Okay, and then yes, to an extent, this looks like a big mumble jumble, but the key is these algorithms are all sequential at least. Okay, if they're not, well, they're at least sequential. So if you want to know if there's a parallel algorithm of it, look for, on this website, look for something saying execution policy as the first argument of sort. We can see that right here, and that they've identified on the right that this is item number 4. It's been defined since C++ 17, so we're good. And if we look down here, we can see that items 2 and 4 are the same as 1 and 3, but executed according to policy. Okay. Now for parallel algorithms, there are, in C++ 17, 3 policies: sequential, SEQ, par for parallel, and par_unSEQ for parallel unsequenced, and that is for parallel and vectorization together. So in the next standard, there should be one just called unsequenced for vectorized, but not parallel, sequential vectorization. So that's how you find out if there's a parallel algorithm. But first, figure out which algorithm you want to use, and then you can figure out the parallel algorithm bit by reading further and exploring it. If you have you want to worry about the header, you need to download the open source code. You want to do development on your own computer or whatever. If you're using Microsoft Visual Studio, though, it already supports this. You don't have to do it. But any other compiler that supports C++ 17, you need to run git clone and clone that. I cloned it into a directory called Intel Parallel STL. So this way, when I compiled my code here, let's take the GCC 9 version. There we go. Make GCC, my apologies, ISO. You can see on the command line here, I have -I to include the include directory. So the parallel STL does not need any special building. You just include the include directory in your search path, and you're good to go.